Okay, so this video is dealing with section 4.2, which is starting to talk about exponential functions. So let's just kind of review some things that we kind of already know, but also some kind of new things here. So if we have a raised to the m over n, so the exponent is a fraction. Remember that the numerator is the power that a gets raised to, and that the denominator is the root or index. And also, we can do the nth root of a to the m, or we can do the nth root of a, and then raise that to the m power. So sometimes it's easier to take the nth root first, and then raise it to the m power. Now, normally we could say like, oh yeah, these are the equivalent. There are sometimes when this causes a problem that these are not possible, the same thing, because if, for example, a is negative and n is even, then that's a problem, right? We can't take the second root or square root of a negative number. But if m is even, then maybe that negative would go away. So it would work here, because we take that negative and raise it to an even power, the negative would go away. Then we could take the nth root of it. But, except for that condition when maybe a is negative and n happens to be even, then we'll, just assume that we can kind of do one or the other first, whichever is more useful. So if we have something like 81 raised to the 3/4 power, then that's the fourth root of 81 cubed. But of course, 81 is already kind of big. We don't want to cube it and then try to take the fourth root of it. Instead, probably we'd want to take the fourth root first, and 81 is a perfect fourth power. So we would think of that as what? Fourth root of 81, well, that's just 3. And then we have 3 cubed. So it's much easier to take the fourth power first in most cases here, and then cube it. So that looks like what, 27? Okay. Next thing, if a raised to the b power is equal to a raised to the c power, that's true if and only if. So that means, that's what we call a biconditional. You might remember that from geometry class. If and only if means if this is true, I can write this, or if this is true, I know this is true. And so if we have exponents, we have variables in the exponents, we can pull those variables out of the exponent if the two bases are the same. So the two bases are the same, and we raise it to this power, so we can set this exponent equal to this exponent, and then we could just solve that equation. All right, number 3, if a is greater than 1, and now we know that m is less than n, then that means a raised to the m will be less than a raised to the n. So for example, if a is 2, and we have 3, which is less than 4, so that means 2 raised to the third power is less than 2 raised to the fourth power. And then if a is less than 1, and again, m is less than n, then a to the m will be greater than a to the n. And so let's go through the example. If a is 1/2, so 1/2 to the third, that's 1/8. That's going to be greater than 1/2 to the fourth, which is 1/16. Okay, so if a is greater than 1, then of course the bigger number is going to make that exponent even bigger. But if a is less than 1, the bigger exponent actually makes it smaller. Okay. So an exponential function in general, f of x equals a to the x. A must be greater than 0, can't be negative for it to be an exponential function. And a can also not equal 1. If it can't really be 0 either, because then it's just going to be 0, right? I mean, in theory it could be, but you're going to see that a is not going to be 0, nor can it be 1, because if it's 1, then 1 raised to any power is 1, and 0 it makes it it's 0 as well. 0 raised to any power is 0. All right, so but it can't be negative because then it's not really going to be a exponential function. You think about it, sometimes when we raise it to an even power, then a would go away, and so it would kind of flip-flop. So a is going to be greater than 0. A cannot equal 1. All right, so let's, for a particular function, f of x equals 3 to the x, figure out what those 4 things are. I would suggest pausing the video and then doing them and then starting the video back up. All right, so I'm going to go ahead and work through these. So this is going to be 3 raised to the negative 2 power. And you remember a negative exponent means we're just going to take it down. So it's 1 over 3 squared to get rid of that negative exponent. That's just 1 over 9. All right. 3, this one is going to be equal to 3 to the 5th power. That's just 243. All right, this one is 3 raised to the 3/2 power. And that's going to be the square root of 3 cubed. We could write that as the square root of 27, but we could just bring 2 of the 3's, would form 1 out in front. So we could just write this as 3 square root of 3. All right, and this one, you really are just going to need a calculator for this one. It means 3 raised to the 2.15 power. So you would just take your calculator and take 3 and raise it using your little caret function in your calculator. And that's approximately, we used a little squiggly equal sign, approximately 10.61. Okay. Generally, we won't ask, we're not going to have you do this very often, but we certainly will have you use fractions and integers, raise bases to certain powers that are integers or fractions. All right. So let's look at making a little graph here. If we know the graph f of x equals 3 to the x, it says C graph at the right, but we're going to actually graph it over here. There are several important details to point out. All right, so first let's make a graph. So think about x values. So this will be the x, this will be f of x. So what if x is 0? If x is 0, then anything raised to the 0 power is 1. So we can plot that point here. And then what if x is 2? Let's start with 1. Sorry, if x is 1, then that's going to be x is 1. F of x would be 3. So we got this point here. And now let's do if x is 2. That jumps it up 3 squared, which is 9. And of course, we could put things in between those, right? I mean, like we could say, try 2.15, right? 2.15 would be here, and we know that's about, up here. 10.6 would be about up here somewhere, all right? But we'll kind of restrict this to just nice integers. All right, what if I put in, what if x is negative 1? So 3 to the negative 1, that's just going to be 1/3. So over here I'm down at 1/3. And then what if it was negative 2? So that's going to be 1/9. That's going to be even closer to 0. And I think you see, if we keep going, you're going to get closer and closer to 0 as x gets very negative, right? So let's kind of sketch this in. We've got an exponential function here. You could see that we're never going to reach 0, so that is going to be asymptotic here, right? So it's going to get closer and closer to it, but never quite hit 0. If I said 3 to the negative 10, that would be 1 over 3 to the 10th. So a really big number on the bottom, but the overall value would be getting closer and closer to 0. All right. All right, so let's talk about some general details of this function. This is a general function. So this is that function we were talking about up above here, right? Where we have f of x equals a to the x, where a is bigger than 1. So if a is bigger than 1, then we'll see this thing kind of explodes, right? As we get bigger and bigger x's, we're raising this value bigger than 1 to a value, and as that x gets bigger and bigger, the whole thing just kind of explodes, okay? And we'll see kind of what it looks like down here when we put something smaller than 1 in. Okay, so as x approaches negative infinity, then that's kind of this notation that we use when we were doing asymptotes. As x approaches negative infinity, f of x is going to approach 0. So there is a horizontal asymptote at y equals 0. The domain is all real numbers. The range can't be negative. You can't get a negative value out of this function. So it's from 0, not inclusive, because there's an asymptote there, 0 up to positive infinity is the range, okay? And it's increasing over the whole interval. Seems kind of flat over here, but it is, if you go to the right, it is higher up. Over on the left, it's closer to 0 than it is on the right. And then also, this is what we would refer to as, in the last chapter, as a one-to-one function. All right, so the inverse of this function would itself also be a function. All right, so it's a one-to-one function. All right, let's look now at a situation where the base a is something between 0 and 1, in this case 1/3. So let's plot a couple points again. So let's make it 0 this time. So x equals 0. We know it's 1 again. If we make x 1, that's just 1/3. If x is 2, then that's going to be 1/9. That's even closer to 0. So you can probably see we get closer and closer to 0 as we get over further and further. And so that's just going to be asymptotic in that side again. If I put a -1 in here, so we have 1/3, we have 1/3 to the -1, so that's just equal to 3. So we've got, at -1, we're at 3. And then if this was 2, then you'd bring the 3 up and square it, so that's going to be 9, right? So at -2, I'm up here at 9. All right, so let's kind of sketch that in. And you can see this is very similar in shape to the previous one, except it is reversed, right? It's a reflection about the y-axis. We'll talk about that more in a second. All right, so we know here in this case, a is between 0 and 1. The y-intercept is the same as the y-intercept we saw up above, 0, 1, 0, 1. As x goes to infinity this time, the function gets closer and closer to 0. And again, we have a horizontal asymptote at 0. The domain is all real numbers. The range, again, is 0 to infinity. It's decreasing this time on the whole set of numbers, on the whole real number system, right, on all possible values. So it's decreasing for its entirety. And then again, this function and its inverse are also functions, so that means that this is a one-to-one function. Now you might kind of look at this. This should look kind of familiar, that these two things are reflections of each other, right, across the y-axis. So if you remember back in our transformations of functions, we looked at when does that happen. And so if we think about, f of x and g of x are just transformations of each other. So f of x is just the f of negative x. So if I take f of x, and instead of f of x, I put f of negative x. So remember what happens when I put a negative coefficient in front of the x. That's when we flipped it about the horizontal, right? And so if I put a negative, f of x, I put a negative x in to this function here, up here. So I put a negative x in to this function, then I really just get g of x. Okay? And so it kind of makes sense that these things should be reflective because 1 is just the negative x of the other function. All right, so evaluating the other function at negative x gives us g of x. All right, so using that idea, we should maybe be able to plot some of these. Right? So what if can we plot what f of x of 2 to the x is, right? So that would look a lot like this one, but 1/2, that's going to make it descending, like decreasing function. So again, if I put a 0 in for x, I get a 1. If I put a 1 in for x, I get 1/2. Put a 2 in, I get a 1/4. At 1, I get 2. At 2, I get 4. At negative 2, sorry, negative 2, I get 4. At negative 3, I get 8. All right, so we can draw this one in here. It should be decreasing over its whole function. Again, has an asymptote at y equals 0. All right, now, what would I do to this function to get this function? Well, we just shift it up 1. All right, notice I kind of brought the x-axis down, so it's really the exact same spot. So instead of being at 1, I'm at 2. Instead of being at 1/2, I'm 1.5. Instead of 1/4, I'm 1.25. And so instead of being at 2, I'm at 3. Instead of being at 4, I'm at 5. And I'm at 9. So it really is the same exact function, only that it has a horizontal asymptote at 1 now. Everything just shifted up 1. All right, now when I put the negative 1 in the x, remember that moves things in the left and the right, and the opposite of what you thought. Now it's 2, not 1/2, so we can't really use this function, but it's the flip of this function, right? So the parent function would be at 1, at 2, at 4, at 8, right? So now what is x minus 1 going to do? So let's think about it. Let's put a 0 in for x, and that's going to be 2 to the negative 1, so that's going to be 1/2. So at 0, I'm at 1/2. Now when I put a 1 in, that makes the exponent 0. Anything raised to 0 is 1. All right, and so you can see that this would be a normal f of x equals 2 to the x, would be sort of the parent function, and this is simply going to be a shift to the right. Remember, it's in with the x, so it goes horizontally, and it's negative, so it does the opposite of kind of what you intuitively would think. All right, and then if I put a 2 in, that's going to be 2 minus 1, so that's just going to give me a 2. 3 is going to give me a 4. 4 is going to give me an 8. All right, and then we can go over here and put a negative 1 in. If I put a negative 1 in, that's 2 to the negative 2, so that's a 4th. All right, and so let's just kind of sketch that in. So we're doing sort of a transformation again here, so you don't have to really plot all the points. If you kind of know what this function looks like, then this is just a translation of all the points exactly 1 unit to the right. Okay, and then what would this one be? So compared to this parent function, what's happening? This parent function over here is getting moved horizontally, left 1, and down 2. All right, so something that would have been here at, if we put this 2 is raised to the 0 power, we're at 1, but we're shifting left 1 and down 2. So we should be here. For this function, we would have been at 1, 2, and we're going to go over 1, down 2, so we would have it 0. And you can always, of course, double check one of these. So let's put 0 in. 0 in for this gives us 2 to the 1, which is 2, minus 2, which gave us our 0. All right? And so if you think if at 2, this one raised to 2 would be 4, so we would be 2, 4. We're going to go over 1, down 2. Okay. Or again, you could just plug the values in here. So let's do this 2, since we don't have a 3. But if we put a 3 in, we'd be up here at 8. We're going to go down 1, to the right 1, down 2, so we would be at 6. But we can double check that by putting 2 into this function. 2 plus 1 is 3. 2 to the 3 is 8. And then minus 2 is 6. Okay. And then let's see, if we put a negative 1 into the parent function, that would give us 1/2. So we would be here at 1/2. We're going to go over 1, down 2, 1, and we're here at 2. And then I think you can see the next one would be down a 4th below that. So, so let's sketch that in. Of course, the horizontal asymptote here is decreasing by 2. So we're down here. The horizontal asymptote is at y equals -2 this time. All right, let's do the first couple of problems then on page 2. All right, so we're solving some equations here. So these are exponential equations, and so it's a little tricky sometimes to get this variable out of the exponent. And so this is kind of the first time we've been solving equations that have variables in the exponents. But we want to use, we want to use the rule that we talked about here, that if the bases are the same, then we can just set the exponents equal to each other. And that's really what we want to do here. So the variable is up in the exponent. I need to write this as 5 to some power. That way I can set my x and this expression equal to each other. So 1 over 125 has to be changed into 5 raised to some power. So think about what that is. So we write 5 to the x equals 5 to the -3rd power. All right, so because 5 to the 3rd is 125, 5 to the -3rd is 1 over 125. All right, so that means x will be equal to -3. All right, and then you would solve that equation. I mean, we set this equal to this, but I mean that is itself the solution. So if that wasn't, x by itself, then you would just solve that. Okay, so let's look at this. We have 2 to some power and 8 to some power. Now we need to make these two things, these two bases, the same. Now, one thing that people say is, well, let's multiply this by 4. Well, that doesn't really work because I would also have to multiply this side by 4. But that doesn't work. I can't say 2 to the x times 4 to some other power, right? It just doesn't work, right? In order to multiply two things, the bases really, they have different exponents. The bases have to be the same. So I would have to multiply that by 2 squared. I could do that, 2 squared. And when I multiply the two bases, I would add the exponents. But the problem is, I would also have to multiply this side by 2 to the 2. And that wouldn't help because then that makes, this thing more complicated as well. So we can't take the bases, they can't take the 2 and make it larger, but you can write the 8 as a 2 to some power. And that's really what you have to do. Now, these are simpler cases where you only have to change one of these bases, but sometimes you might have 2 bases. Both bases need to be changed. One's a 4 and one's an 8. You have to change them both to 2s, so be careful. You might see some of those in homework. All right, so we're going to leave this one as 2 to the x plus 4. And then this one has to be written as 8, it has 2, change the 8 to 2 to the 3rd, and then that's being raised to the x minus 6. Now be careful without putting kind of these parentheses in here. Often people write it and it's 2 to the, and then they write 3x minus 6. This 3, there's really almost like a parentheses around here. You got to distribute this 3 to both things. Common mistake, you don't turn that into -18. It's got to be negative 18. And people end up leaving it as 3x minus 6. That's wrong, so be careful with that. So on the left, I have 2 to the x plus 4 equals 2 to the 3x minus 18. And then we say x plus 4 equals 3x minus 18. And now I have an expression. Now I can solve this, right? So let's bring the x over here. That's 2x. And take the 18 over there. That's 22. So it looks like x equals 11. Okay? All right, try the next one. All right, so C is sort of a trick question. It's not that it can't be solved. We don't know how to solve it yet. And really, this is sort of a motivational type question. We'll be able to solve this question by the end of the chapter, but we can't solve it now. This problem is the reason why we need logarithms. We have to be able to understand and learn logarithms, which is our next section, in order to solve this. The problem is I cannot make these bases the same. There is no number. I can't write 7 as 3 to some number. I mean, I could. I just don't know what that number is. It's not a nice, easy number. So we would have to, if we were going to solve this, we would have to be able to take 7 and write it as 3 to some power. We could approximate that with our calculators, but we just don't know. Like, there's no exact answer for that. So there's no way to solve this yet. And we will be able to solve it by the end of the chapter, though, but we just can't do it yet. So that was sort of a trick question, but a motivational type question to encourage you and to understand, like, why are we doing logarithms? It's because of this problem. We need logarithms to solve that. Okay, next question, D. In this case, the variable x is not in the exponent, but x has a fractional exponent in it. So it's not technically what we would consider an exponential function, but it is a function with exponents in it. All right, so how would we do this? Remember, we want to get this x by itself. We want to take x to the 2/3. We did this previous chapters. We will raise both sides of this to the 3/2 power. 2/3 times 3/2 is just 1, so we have x to the 1, and then we have to do the same thing to this side, of course, 3/2, and so that's the square root of 25, which is 5 cubed, and that will be 125. Okay, so if you need to, you can write that as, square root of 25 and then cube it. Certainly you can do that, but it will be good that you can see, like, oh, that 2 down there, that's the square root. The square root of 25 is 5, cubed is 125. So if you get comfortable using this and not having to always rewrite it, that's probably a good idea. All right, so this is the end of this video for the first part of 4.2. The homework 4.2.1 is due next class.